All right, we're back, and I've added some things over here while we were gone. This is just adding the things that we had been using over in our truth tables here, relating the statements here to sets and whether we have something in a set and what set we're talking about. Notice, by the way, that the new compound statement we constructed here, it's a little bit complicated what the set is that X would be in. And so it says here that if P is that X is in A and Q is that X is in B, then this compound statement says X is in A or B, A union B, but not in both. So it's in A union B, so this is false, but it's not in both, so this is false. And that's what this slash here means. This is set difference. So that really means this set minus this set intersected with the complement of this set. We'll see that again as we go forward. So over here, we have a kind of nascent truth table, a potential truth table, but all I've got is the 4 possible truth values of the constituent statements. And so what we're going to do here is look at the compound statement that is an implication. And so that we write like this. And the truth value, we define the truth value of this to be true here, false here, true here, and true here. And it's an implication, and we read this as P implies Q, or if P is true, then Q is true. So let me actually do that here also. Let's say this is implies, or we could also say it is if P, then Q. 2 different ways we would say that. And so this defines the truth value of this compound statement, of this symbol. Remember, this is symbolic logic. Now, note that let's write in here Q or not P. So I'm writing down a different compound statement, one that we haven't seen before, but this one is clearly put together with the 2 of the 3 basic connecting operations, 2 of the 3 basic operations on simple statements to give us compound statements. Here we have the disjunction, and here we have the negation. And you recall, I said we could get any of the 16 combinations of truth values with just disjunction, conjunction, and negation. And so that means that we should be able to get these 4 truth values somehow like this. And indeed, you can check easily here that Q or not P, well, Q is true, so this is true. Here, Q is false, and not P is also false. P is true, so this is false in this case. Here I have Q is true and not P is also true, so this is true. And here Q is false, but not P is true, so true. So note that this combination of truth values is exactly the same as this one here. Both of them are new in the sense they haven't shown up as one of the first 7 that we did. So this is an 8th one if you like. But these are the same. So these are therefore said to be logically equivalent. So let's write that down here. Let's say P implies Q, that compound statement. In fact, we even say equals Q or not P. And by equals here, we mean they have the same combination of truth values. Whatever the truth value happens to be of this, that's going to have the same truth value in every instance of a P and a Q. So these are the same in this regard. And notice that in terms of sets, if this is X is in A and this is X is in B, then this is that if X is in A, then X is also in B, which is the same as saying A is a subset of B. That is, X in A implies X in B. And of course, I've written it under this one, but it's the same over here because they're the same compound statements. They look different. We constructed them differently, but the truth values are exactly the same. And so over here, I want to keep track of these. So here I'm going to write P implies Q, and that is T, F, T, T. Let's make sure I got that right, yes. And that's like A is a subset of B. I'll leave out this one here, just in the interest of space. And so let's look at another possibility here. Let's look at, suppose I take not P and I'm squeezing this in here to get it so that it, here, let me take this off and try to do a little better job of squeezing it in. Let's say this is going to be not P or not Q. Well, notice that's really the same as this. The not P is not P. I just reversed the order, but that's not a problem. And the not Q is twice negating Q, which gives me Q. But also notice that this has the form that would give me not Q implies not P. You see, the second one of these is not Q. First is not P. So if we work that out over here, we're going to find that the truth values are T, F, T, and T. This is exactly the same. And so that is not Q implies not P. And so I don't have space to write that here, but I'm going to write it over here. So this is not Q implies not P, and the truth values are T, F, T, and T. So here, for the first time in the table over here, and of course this would still be A as a subset of B, I would say if I have an X that's not in B, then it's not in A. A is a subset of B. So actually, these, let me maybe use a different color here. These are identical. And of course, I have yet another one that's identical. I just didn't put it in over here because we don't really use this sort of as a special notation. Instead we use this, okay? But here we actually do use this, and this actually is kind of important because often when we're trying to prove something, let's say a theorem, the theorem might be, well, if some statement P is true, then it has to follow that some other statement Q is true, and we want to prove that. Well, often the easiest way to prove it is instead to prove that if the statement Q is false, then the statement P has to be false. And that's, we refer to that as a proof by contradiction or indirect proof. But this compound statement is called the contrapositive of this compound statement. So let's actually write that in here too, that This is the contrapositive of P implies Q. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, not 9 because these are identical. So we have 8 of the 16 possible combinations of truth values. And now let's look at a few more. And here I'm not going to write any more separate truth tables. I'm going to just do all the truth tables over here in this sort of big table. So let's come down here and let's look at the negation of P or Q. Okay? Well, we can figure out what the truth values are. We could do that in a separate truth table, but we can do it here just as easily. We have P or Q, and we have the negation of that. So in other words, here we have P or Q, and so the negation of P or Q is going to reverse all of the truth values. So it's going to be F, 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 and T. Indeed, that's what we have. F, 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 and T. For now, at least, I'm not going to write down the corresponding notions for sets over here. But I am going to say, let's look at, instead now, let's look at not P and, there's supposed to be a caret there, folks, and not Q. Okay, let's see what the truth value of that compound statement is. Well, we need to look here, not P and not Q. So here we have not P and not Q. So they're both, not P and not Q are both false. So this would be false. And coming across, I have not P and not Q. Well, they're not both true. They're not both true. So these are both false. The one place where not P and not Q are both true statements here is the situation where both P and Q are false. So not P and not Q are both true. So this is true. And again, just like over here, notice that I have got two different, seemingly different, compound statements, but they have exactly the same combination of truth values. So these are, again, logically equivalent, just like these are all logically equivalent. So let's actually circle these as well, because these are just two versions of the same thing. I'm just leaving this blank for now. Let's do one more. Let's look at the negation of P and Q. All right. So the negation of P and Q, well, here's P and Q here. And the negation of that is going to have truth value F, T, T, T. So we have F, T, T, T. And so let's just stop for a minute and see if this kind of makes sense. If P and Q are both true, then the negation of that is going to be false. That would be here. If either one of these is false, then this will be false, but its negation will be true. So these should both be true. And if these are both false, then the conjunction is going to be false, and the negation will be true. So this is true, right? So we did it here by kind of just looking at the truth values, and here we kind of reasoned it out a little bit. And so let's now look at another compound statement, which is going to be not P or not Q. Again, we can easily get the truth values here. Here we have not P, here we have not Q, and so here neither one is true. I'm sorry, that they're both both not P and not Q are false here. So this is false. And it looks like we're going to probably end up with T's across here. Let's check that out. We have not P or not Q, not P, not Q is true. So T. Not P or not Q, not P is true. True. Not P or not Q, they're both true. So true. So again, just like the one above it, we've got, again, two identical combinations of truth values. So we have two compound statements that are, again, logically equivalent. And in fact, these two, the logical equivalents, and let me write those over here, or at least I'll write one of them. I'll write the first one here. This says not P or Q equals not P and not Q. Oh, I'll write them both. Let's do the other one too. Not P and Q equals not P or not Q. These are what we call De Morgan's laws, and we could say they're De Morgan's laws for logic. We also have De Morgan's laws for sets, and they're really the same. They're really the same laws. It's just translating the compound statements into statements about sets, like over here. And so, actually, this would be the complement of A intersect B is equal to the complement of A union the complement of B, and this would be the complement of A intersect B is equal to the complement of A union the complement of B. And so these two statements about the relation between sets formed by union, intersection, and complementing are De Morgan's laws for sets that correspond exactly, of course, to De Morgan's laws for logic, where instead of intersection, union, and complement, we have conjunction, disjunction, and negation. And so those are ones that you, if you don't already kind of know them by heart, if you don't have these kind of already internalized, you hopefully will get them internalized pretty soon, because we use these all the time. And of course, we also use this contrapositive idea all the time as well. So now let's just sum up what we've done here. So what we have is we've formed a bunch of compound statements from our two constituent statements, P and Q. We've done all of this really by just using negation, conjunction, and disjunction, the ones that don't seem to be explicitly formed from conjunction, disjunction, and negation, like this one, I guess just those two are equivalent to ones that are formed by just using conjunction, disjunction, and negation. And now I note that I've actually left out one of the compound statements I want to write in here, and that's the last one. Let's do that here, and let's put in here P if and only if Q. So that's how we would say this. This is the contrapositive of an implication, and this we would say is, we would say if and only if for this operation between the constituent or elementary statements. And so this is actually the same as, was several things we could write that would be equivalent to this. This is the same is P implies Q and Q implies P. So that is going to be, and in fact, you can also check, I won't write this down, but you can check that this is equivalent to the negation of this. So let me just write that off on the side here. The negation of P, P exclusive OR with Q is exactly the same as these down here. So we can see by combining P implies Q and not this, but Q implies P, that this is going to be true when we have T, F, F, and T. P is true if and only if Q is true. So here, if P is true, Q has to be true. If P is false, Q has to be false. If P is true and Q is false, P is false, Q is true, then this compound is false. So this would correspond to the set A being equal to the set B. And of course, this is exactly the same. Okay, so again, let me put rectangle around all of this because these are logically equivalent. So each of the 4 places where I have a blue rectangle around here would be a case where we have blue is logically equivalent compound statements. And so altogether, how many do we have? One, not that they're all compound statements, these aren't, but we do get here our two basic statements give us our combination of 4 truth values. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 of the 16 possible combinations of truth values. I'll leave it as an exercise for you to construct compound statements from just conjunction, disjunction, and negation to obtain the remaining 5 combinations of truth values here. So I think at this point we have probably gone on pretty long in this lecture, and so I think we will take a break here, and then we'll come back and we'll finish the lecture in a few moments. Okay, so see you in a few moments.